Now that we know what to do when we have the clues, we need to figure out how to actually find the clues. First thing we want to know is, what is the domain? Well, we already know how to do that. We did that at the beginning of the semester. How about the x and y intercepts? Well, the x-intercept is when y equals 0, and the y-intercept is when x equals 0. So that's pretty straightforward. Asymptotes. The vertical asymptotes are where the bottom equals 0 and the top doesn't, and horizontal asymptotes is where you look at the limit as x approaches infinity. You're only going to have vertical asymptotes if you have rational functions, like something over something. Horizontal asymptotes, if the top has smaller degree than the bottom, your horizontal asymptote will be y equals 0. If the degrees are the same, you're going to have the ratio of the leading coefficients, and if the degree of the top is bigger than the bottom, you don't officially have a horizontal asymptote, but you might have a slant asymptote. Next, the first derivative. It tells us about increasing and decreasing. The function is increasing when the first derivative is positive, it's decreasing when the first derivative is negative, and you will have a relative or local extrema if your derivative is positive on one side and negative on the other. Second derivative tells us about curviness. We have two choices, concave up and concave down, and we'll talk more about that in a second. You have concave up when the second derivative is positive, and you have concave down when the second derivative is negative. You have an inflection point when you have different concavities on either side of that point. So f double prime is positive on one side and negative on the other. So let's look at an example. Here's my function. I've got x cubed minus 2x squared minus 5x plus 6. I went ahead and factored it. We know the domain is the reals. It's a cubic, so we know it's going to look something like this. What can I tell? Well, we've got the intercepts. The domain is the reals. Our x-intercept are the roots of this equation, so at 1 and negative 2 and 3, so 1, 0, negative 2, 0, 3, 0. The y-intercept, you plug a 0 into your function, and what gets popped out is a 6, so my y-intercept is 0, 6. Since this is a polynomial, you have no asymptotes. This is what it looks like. A critical point of a function is a point in the domain where f prime equals 0 or f prime does not exist. Looking at this picture, I can see the places where the derivative is 0 are these two places in green. I can see the derivative doesn't exist where it is pointy. If the function is increasing on one side of a critical point and decreasing on the other, we have an extrema. So let's look at this example. We have f of x equals x cubed minus 3x squared plus 1. Taking the derivative, I get 3x squared minus 6x. I set equal to 0 to find the critical points. There's no place in the domain where the derivative does not exist. Factoring, my two critical points are at 0 and 2. Let's see what they are. You can check and see that the derivative in these three sections are positive, negative, and then positive. So I have increasing, then decreasing, and then increasing. At 0, I have increasing on one side and decreasing on the other, which means at this point we have a relative max. At 2, it's decreasing on the left and increasing on the right. So at this point we have a relative min. Let's look at the second derivative. The second derivative tells me about curviness. Now suppose you know the function is increasing. How do you connect the dots? You can either draw the line straight, you can bow this way or bow that way. What's the difference? Well, the first one, the second derivative is 0. The second one, the second derivative is positive, and the third one, it's negative. The first one is just a straight line, but the other two are curvy. The second derivative is positive, you have concave up, and the second derivative is negative, you have concave down. Similarly, if you have 2 points and you know the function is decreasing, how do you connect these dots? If the second derivative is 0, you have a line. If the second derivative is positive, you have concave up. And if the second derivative is negative, you have concave down. So let's get some definitions here. Concavity. If f double prime is positive for all x in an interval I, then f of x is concave up on that interval I. If f double prime is negative for all x in an interval I, then f of x is concave down on that interval I. You don't have anything like a critical point for the second derivative, and that really pisses me off. It's a pain in the butt. You have a possible inflection point if the second derivative is 0 or does not exist. So just like with the first derivative, we want to find those points, and then we determine if they're actually inflection points or not. They're inflection points if you're concave up on one side and concave down on the other. So let's look at this example. I have y equals x to the fourth minus 4x cubed. I need to take two derivatives if I'm going to look at concavity. So there's my first derivative and my second. I need to set equal to 0. There's no place where it doesn't exist because I've got a nice pretty polynomial. So factoring it, I get 12 times x minus 1 times x plus 1. So my possible inflection points are x equals plus or minus 1. Setting up my little chart here, I can check the points in between, and I see that the second derivative is positive in that first section, negative in the second section, and positive in the third section, which means my concavity is up, down, up. Now at -1, it's concave up on one side and concave down on the other, which means at this point I have an inflection point. Also at 1, the same thing happens. So I've got 2 inflection points, and that's how you find out about the curviness. We're going to spend time finding the information, and then we'll talk about putting it all together.